Hey there, and welcome back to the deep dive. So, we've spent a lot of time digging into large language models. And yeah, for years, that pretty much meant talking about transformers. I mean, they've been the main game in town, right? Powering everything from, GPT-2 way back when, right up to the models you're probably using today. But things are moving incredibly fast in AI. Seriously fast. New architectures are popping up and they're performing, well, just as well, sometimes even better. It's really challenging that transformer dominance. And one name that keeps coming up, making some real waves, is Mamba. Now, these Mamba models, they get great results, but they work very differently inside. They actually completely ditch the attention mechanism we talk about so much and replace it with something called selective state-space models. So that leads us to the big question, the mystery we're really diving into today. How do these newer models, like Mamba, actually handle information internally? Especially basic facts, like Paris is the capital of France. How does that work inside Mamba? And maybe even more importantly, how do we even look inside a system that doesn't have those attention pathways we've sort of learned how to map?
That's exactly the puzzle, isn't it? And it's the core challenge tackled by a really fascinating recent research paper. It's titled Mamba Knockout for Unraveling Factual Information Flow. This paper basically introduces some pretty sophisticated new ways to, well, peer inside Mamba's workings to really understand how it processes factual knowledge. So for this deep dive, we've got our usual stack, the paper itself, detailed briefings, our own notes, and we've sifted through it all. Our mission really is to pull out the key insights, the most important nuggets from this complex research. We want to help you get up to speed quickly on these cutting edge models and the academic innovations being used to decode them.
Right? It's like trying to draw a map of Mamba's brain specifically for facts, using some tricks learned from Transformers, sure, but also inventing completely new tools. It's a real look under the hood. Okay, let's dig in. So, just to set the scene a bit, for a long time, researchers were super focused on cracking open the transformer black box, right? We started figuring things out like where facts seem to get stored, often pinpointing those MLP layers. And we developed techniques, clever ways to trace how information actually flows around inside. Things like attention knockout, causal tracing. But these tools were mostly built around probing that attention mechanism because, well, that was the heart of the transformer.
Exactly. But then, like you said, Mamba arrived on the scene, introduced by Gu and Dao in 2023, then refined with Mamba-2 in 2024. And these models, they perform really well, sometimes even outperforming transformers, especially on longer chunks of text. But crucially, they do it by swapping attention for these selective state space models, or SSMs. And this completely different architecture meant, well, our hard-won interpretability tools for transformers, they just didn't apply directly. It threw up a whole new scientific challenge. How do we track information flow now? Okay, and here's where it is really, really interesting. This is the crucial bit of academic work that actually made this study possible. Some very recent theoretical research, specifically work by Ali and colleagues in 2024, and also Dao and Gu again in 2024, provided a massive breakthrough. They managed to show that these selective SSMs, even though the math looks different, can actually be understood using an attention-like perspective. Even more powerful, they proved a specific class of these SSMs is mathematically equivalent to a type of linear attention transformer. This theoretical bridge, this connection, is absolutely fundamental. It's the foundation stone. It basically said, hey, look, there's a hidden relationship here, which then allowed researchers to even consider adapting methods across architectures. It's a brilliant piece of theoretical insight.
Right. You absolutely needed that connection first, that moment linking SSMs back, even loosely, to attention before you could design the probes. And the main probe they adapted was this idea of knockout. The basic concept is, well, pretty straightforward actually. You intentionally break something inside the model. Like you block the information flowing between two specific words, say the subject and the last word, at a particular fire. And then you just check. Can the model still get the factual answer right? They used a specific data set for this counterfact, which is full of these factual recall questions. And they made sure the model knew the answer before they messed with it so they could really isolate the effect of their intervention.
Precisely. And taking attention knockout, which, as you said, was developed for transformers by Java and others in 2023 and making it work for Mamba, that took real technical innovation, building directly on that theoretical bridge we just talked about. For Mamba-1, they had to lean on that hidden attention idea from Ali et al. You can sort of picture Mamba's process as implicitly calculating a score between tokens. It's like attention in its effect, but calculated differently. So the clever part was figuring out how to manipulate that implicit score, essentially finding a way within Mamba's math to zero out the connection strength between token I and token J, mimicking what you do with attention weights. Now, for Mamba-2, the adaptation was a bit different, but just as clever. It used that link to linear attention shown by Dao and Gu. Since Mamba-2's SSM layer has this mathematical interpretation as a kind of masked linear attention, they found they could manipulate it more directly, closer to actually zeroing out attention weights. So that was another key technical step, you see. They had to tailor the intervention specifically for each Mamba variant, guided by that latest theory. They didn't just copy-paste, they re-engineered the method. But, and this is really important for the academic innovation part, they didn't just adapt old methods. They also introduced something genuinely novel, specifically for SSMs, feature knockout. This technique really leverages a unique aspect of how Mamba is built. Inside Mamba, you have these different channels or features that process information somewhat independently. And crucially, each feature has its own decay rate, how quickly it forgets older information. So you can think of it like having different types of memory circuits. Some features decay slowly, they hang on to information from way back in the sequence, they're context dependent. Others decay really fast, they mainly focus on the very recent past, maybe just the last token, more context independent or localized. The innovation of feature knockout is that they figured out how to selectively switch off or zero out the output of just the slow decay features or just the fast decay features layer by layer. This is totally unique to analyzing SSMs. It gives us a brand new lens to understand how these different internal memory types contribute to the model's processing. You just couldn't do quite the same thing in a standard transformer.
Wow, okay, that is a completely new tool then. A specific magnifying glass for Mamba's unique guts. So they've got these knockout tools, the adapted one and the new one. What did they actually find when they started disrupting the flow of factual knowledge? Let's start with that first set of results. Blocking information flow to the final token, where the answer comes out from important earlier tokens, like the subject, the relation word, the very first token, or even, weirdly, the last token itself. What happened?
Okay, so the first big finding here points to a shared characteristic, something that seems consistent across both Mamba models they tested, Mamba-1, Mamba-2, and also the transformer they used for comparison, GPT-2. Consistently, if you blocked information flowing from the subject tokens, like Beats Music, Beats Music is owned by Apple to the last token, especially in the late intermediate layers.
Late intermediate, so like not right at the beginning or end, but maybe two-thirds to most of the way through.
Exactly. Think roughly 60% to 90% through the model's depth. Blocking that subject to last token connection there consistently caused a major drop in the model's ability to predict the correct fact, Apple. This strongly suggests that universally across these architectures, the subject holds critical information for the fact, and it needs to get passed towards the end, specifically in those later processing stages. This actually lines up really well with what previous studies found in transformers, too.
Okay, so that's a common principle. Subject info is key, especially later on. But what about the differences? Where does Mamba diverge?
Right, now for the distinct stuff, the ways Mamba seems to operate differently, revealed by these knockouts. First off, first position bias. We know from earlier work that transformers like GPT-2 often lean heavily on whatever was the very first token in the input sequence, especially in later layers. Blocking info from that first token hurts their performance. But interestingly, the Mamba models in this study, they did not show this strong reliance on the first token. They seem less sensitive to the absolute position, processing information maybe more dynamically based on content.
Huh. So less dependent on the starting point. What else?
Second, how they handle relation tokens. Think the is owned by part. Transformers, like GPT-2, tended to rely more heavily on these relation tokens in the early layers of the model. Mamba models, however, showed their main reliance on relation tokens shifted much later in the processing pipeline. So different strategies for using the query's structure, it seems.
Early versus late reliance on the relation. Okay.
And then there's this really surprising last token phenomenon. This one was genuinely counterintuitive, I think, specifically in Mamba-1 and models built like it. If you blocked the information flowing from the last token back to itself in those later layers.
Wait, from the last token to the last token, like stopping it from influencing itself.
Exactly. You'd expect that to hurt performance, right? Make it harder to finalize the answer. But in Mamba-1, blocking that self-connection in later layers actually caused a significant increase in the probability of getting the right answer. Performance improved.
It got better.
Yeah, often jumping way up, sometimes close to 100% certainty on the correct fact. It's really odd. And this was specific to Mamba-1 and related models. They did not see this effect in Mamba-2 or in the transformer. Normally, blocking that last token connection makes things worse.
Wow. Okay, that is pretty wild. Removing a connection makes it more accurate. Did the paper hazard any guesses as to why that might happen in Mamba-1, even preliminary ones?
They definitely flag it as surprising and something needing more investigation. One tentative idea they float is that maybe, just maybe, in Mamba-1 specific architecture, that late-stage last token self-connection is somehow creating noise or interference. It might be slightly obscuring the strong factual signal that's already arrived from the subject token in earlier layers, so blocking it could be like removing static, letting the correct signal come through more clearly. But yeah, like you said, it's speculative. The definitive why is still an open question based on the sources.
Fascinating stuff. So, taking all that together, it means Mamba and Transformers seem to agree on some basics, like the subject being key late on. But their internal routing strategies, how they handle positional info, or the query structure, or even this weird last token feedback loop, those seem fundamentally different. Mamba isn't just a slight variation. It's got its own unique ways of processing things. Okay, let's circle back to that novel technique, feature knockout. The one looking at Mamba's internal memory circuits based on decay rates. What did that tell us specifically about factual knowledge?
Right, this feature knockout gave a really valuable insight into which specific components inside Mamba are doing the heavy lifting for facts. The core finding, shown conceptually in figures like Figure 6 in the paper, really contrasted those context-dependent and context-independent features. What they found was striking. When they knocked out only the context-dependent features, remember, those are the slow decay ones that hold on to history specifically originating from the subject tokens. The negative hit to performance, the drop in getting the fact right, was almost identical to knocking out all features from the subject tokens.
Wow, so disabling just that one type of feature was almost as bad as disabling everything from the subject.
Exactly. It's strong evidence suggesting these context-dependent features are the primary vehicles carrying that crucial factual information from the subject through the layers to the final prediction point. And conversely, when they knocked out the context-independent features, the fast decay, localized ones again, from the subject tokens, it had almost no impact on factual performance. This really reinforces the idea that their job might be different. Maybe they process the subject token itself locally, but they aren't the main messengers carrying its factual meaning across the network to combine with other information for the final answer. And this is a fantastic academic insight because, as we discussed, it gives a new way to interpret what's happening inside Mamba. It's kind of analogous to how people use attention maps in transformers, but it's tailored to SSMs. It helps pinpoint just types of Mamba's internal machinery are vital for this specific task we're calling facts.
These are really deep, quite academic insights into how these models tick. But let's connect it back. How does this kind of fundamental understanding translate into, practical benefits for people actually building or using these LLMs? Why should knowing this matter?
Yeah, that's a fair question. The source material actually points to several potential practical applications stemming directly from this kind of interpretability work. First up, smarter pruning. Since those context-independent features seem less critical for passing factual information between tokens, maybe they're good candidates to remove. You could potentially prune them out to make Mama models smaller or faster, or use less memory, hopefully without tanking their factual accuracy. The sources mention they often contribute minimally to between token information flow and therefore can be safely pruned.
Okay, efficiency gains. Makes sense. What else?
Second, potentially more efficient fine-tuning or adaptation. If you can use these knockout techniques to identify the absolutely critical context-dependent features or those key subject-to-last token connections in later layers, well, maybe you can do targeted updates. Instead of retraining the whole massive model, you might just tweak these specific crucial parts to teach the model new facts or adapt it to a new task much more efficiently. The paper talk about finding practical leverage points for precise and efficient model adaptation.
Ah, surgical updates rather than a full rebuild.
Exactly. And third, relatedly, it could inform targeted model editing. Techniques exist for transformers, like Rome or Mehmet, to directly go in and change a stored fact. Knowing where factual information seems to flow and reside in Mamba, thanks to these knockout studies, could guide how you'd adapt those editing techniques for Mamba models. You know where to intervene.
Right, so it gives us handles to understand, optimize, and modify these new architectures. Very cool. But like any study, it can't answer everything. What limitations did the authors themselves point out about this knockout approach?
Yeah, they were quite clear about the boundaries. While knockout is great for showing causality if I break X, it affects Y. It doesn't necessarily capture the entire complex web of information flow. It mainly looks at flow within sort of continuous windows and might miss information taking more convoluted paths. And crucially, it tells you that a connection matters, but not what specific information is traveling along it. Is it the subject's identity, its relationship to the object? We don't know the content, just the importance of the pathway.
Okay, so it's about the plumbing, not the water flowing through it.
Kind of, yeah. Also, the method focuses heavily on the between token flow because that's what SSMs really differ from attention. It doesn't fully analyze other parts of the Mamba block, like certain internal gates or convolutions that don't directly involve passing info between specific token positions. And finally, while it highlights these fascinating patterns shared and distinct, it doesn't fully explain the why. Why do both architectures settle on using late layers for subject info? What deep-seated architectural properties or inductive biases lead to Mamba not having the first position bias or having that weird last token effect in Mamba-1? Those deeper why questions remain.
Got it. Still, this has been a really illuminating deep dive into some genuinely cutting-edge research. So to kind of wrap up, this paper did some impressive work developing and applying these knockout tools, adapting old ones, inventing new ones to get a look inside Mamba. And it showed us there are these universal patterns for handling facts, like that late layer subject importance shared with transformers. But it also uncovered really interesting Mamba-specific ways of doing things, especially around positional info and that strange last token behavior.
Absolutely. And I really think that novel feature knockout technique stands out. It's exciting because it uses Mamba's unique internal structure, those decay rates, as a way to understand it. It gives us a new analytical lens, highlighting how crucial those context-dependent slow decay features are for moving facts around inside the model. That's a real step forward for SSM interpretability.
Yeah, and this kind of academic work, figuring out the nuts and bolts, is just so crucial, isn't it? It helps us build a more unified picture of how all these different LLM architectures actually work, finding out shared rules, but also appreciating the unique strategies. That's how we learn to build better models, maybe even combine the best of different worlds eventually.
I agree completely. And it really leaves you thinking especially about that surprising Mamba-1 result where blocking a connection helped. It makes you wonder what other counterintuitive things are happening inside these incredibly complex systems. What other hidden dynamics or subtle interactions are shaping their behavior? And if we could truly understand those non-obvious internal processes, what could that unlock? Not just for improving current models, but for our fundamental grasp of how intelligence, artificial or otherwise, actually learns and reasons.
Well, it's a powerful reminder that the quest to really understand these AI minds is far from over.